Today we're going to continue to look at line integrals through vector fields. Today we have a new vector field. The video I did before this, we did a line integral along two different paths, and with that vector field, we noticed that depending on the path we went, we got a different amount of work that was done to us by the vector field. Work, I literally mean work like as in physics. So we're going to investigate this again with a new vector field. Here's generally how we compute line integrals, right? We like this format here, where we plug the parameterized function into the vector field, and we multiply by, well, we don't really multiply, we use a dot product with the derivative of the curve we're moving along. So let's take a look at this problem here. So same vector field, but our line segment is going to go from the point -1, 2 to the point 1, 2. So the first thing you need to do is parameterize that. You should notice that y is always 2 here for both points. So when we go to write our parameterization, x of t can just be t, and y of t is just 2. So you just need to set up what restraints you want to put on t. If we want to make sure that we can get from this point here to this point, then t should go from -1 to 1. Just plug in the points. So for example, if you plug in -1 here into x of t, you get t equals -1. Y would be 2, and that's good because that's this point. And then if we were plugging +1 here, then x would become 1, and y would still be 2, which would give you this point. So this equation for our line segment does the job, so to speak. It goes from the first point to the second point the way we wanted. So let's go ahead and compute that line integral. So here we go. It's going to be line integral from, or integral from -1 to 1. F of r of t means we're going to take this parameterized function over here and we're going to sub it into that vector field. So if we do that, we end up getting t over the square root. X is t, so it's going to be t squared plus 2 squared. What's it, 2 there? And this gets multiplied by I plus y, which is 2 over the square root of t squared plus 2 squared times j. And then this thing's going to get dotted with r prime of t. So that means we go take the derivative of our parameterized function. So let's just not lose track of that. So I'm looking over here now. The derivative of x of t is just 1. So I'm going to have 1 times I plus the derivative of y of t. Well, the derivative of 2 is just 0. So 0 times j. And then we have dt here. Okay. So we're ready to do our dot product. And it's actually going to be pretty nice because that 0 in the y component is going to cancel out and simplify things for us. So here we go. Integral -1 to 1. 1 times this whole expression is just that whole expression. So I get t over the square root of t squared plus 4. And then I'm getting ahead of myself for a minute here. I want to write dt. I just need to make sure, but it's actually pretty easy because when I multiply 0 and this component, I get 0. So there's nothing to add to this. So the integral literally reduces to just that. So now we go back to what we know in our second semester calculus course. We're going to find the derivative, or an antiderivative here. I'm going to use a u substitution. I'm going to let u equal the expression on the bottom because it's inside the square root function, and then du dt is equal to 2 times t. If we try and solve that for dt, we get dt equals, sorry about that, should be du over 2t. And so what we're going to do is we're going to plug this expression in for dt, and we're going to plug this in for u and see what happens. So here we are, integral, wrong pen, I wanted blue here, just to change the colors, why not? So we get integral t on top, square root of u now, and then dt becomes du over 2t. And you know things have gone well if the t cancels for you, which it does here. And so really you have a constant of 1/2. So I'm going to factor that out in front. I'm going to do 1/2 integral 1 over the square root of u du. I'm not going to put any limits of integration yet. I'm going to do the antiderivative first, plug back in what u is, and then plug back in my limits of integration. So I'm going to rewrite this as 1/2 integral u to the negative 1/2 du. So when we go to take the antiderivative of that, we add 1 to our exponent, so you get u to the 1/2 over 1/2. You always divide by your exponent, but then there's a 1/2 in front as a constant. So interestingly, these cancel. So very, very nice thing here. You just get the square root of u, which is really the square root of, let's not forget here, we started this whole thing by letting u, oops, sorry about that, letting u equal t squared plus 4. So that's what's going to happen here. I'm going to have t squared plus 4. And then we're going to evaluate that from 0 to 1. And if we plug in 1 there, we get the square root of 5. If we plug in 0 there, we get minus the square root of 4. So everything's said and done, we get the square root of 5 minus 2. Okay, so, oops, sorry about that. A little bit of a issue there. So let's just rewrite that for you. Okay, so we have the value of our integrals. This is the amount of work the line or the vector field has done to us as we moved along this path. Okay, so let's look at the same vector field, but this time I'm going to pick a different path that moves between the 2 points. So here you have y equals 1 plus x squared. Parameterizing this is nice and easy. X of t, you just make it equal to t, and y of t is just equal to 1 plus t squared. It's easy to see that if the t were substituted for x here in this lower expression, that you'd get back the equation y equals 1 plus x squared. Let's worry about our domain here. Well, we want to go from -1 less than or equal to t less than or equal to 1. So we can go from the point -1 to the point +1, 2. It's worth just checking. If you plug 1, for example, in here for t, 1 squared is 1 plus the 1 gives you the 2, which is the y coordinate at that point. Okay, so now we have our expression here. This is usually referred to as r of t. And let's go ahead and start to evaluate this line integral. So we know we're going to use this format, right? We're going to take r of t, sub it into our vector field, and then do the dot product with r prime of t. So let's go do that. So our vector field is right up there above, so it's going to be integral. Instead of x, we're going to put t, and it's going to be over the square root of t squared plus 1 plus t squared squared times I. So not as nice to look at as the previous problem we just did. Plus, and then y, so 1 plus t squared over the same denominator again. 1 plus open 1 plus t squared squared times j. So that whole thing there is f of r of t. We're going to dot that with the derivative of r, which is just going to be 1i, that's the derivative of t, plus 2tj, and then this is dt. We're going to go from -1 to 1. Okay, so we have an equation, or I'm sorry, I should say, we have an integral all in one variable t, and it's time now to sort of bash through it. It's certainly not pleasant to look at. We've got to do kind of a crazy dot product. But before I get going with that, let's just simplify the expression under the radical here. Let's do that. So you have t squared plus, And then if we square 1 plus t squared, we get 1 plus 2t squared plus t to the fourth. So this becomes the expression 1 plus 3t squared plus t to the fourth. So we'll just keep that in mind. Let's multiply now. What's nice is I multiply this numerator of t by this 1, and nothing happens, really. So you just get the integral from -1 to 1, and then you have t over the square root of 1 plus 3t squared plus t to the fourth. And then dot product tells you to add to that the product of the y components. So the y components are here. You've got this numerator, 1 plus t squared times 2t. So if we were to multiply those together, we end up getting 2, sorry about that, 2t plus t 2t to the third. So that's what happens there when we distribute that 2t across the top. And then you have the same denominator again. Square root 1 plus 3t squared plus t to the fourth. All right, so far so good. Okay, so let's continue. We'll add those numerators together and then try and go for an antiderivative here. So on the numerator here, we end up getting 3t plus 2t cubed. And then we have our denominator, 1 plus 3t squared plus t to the fourth. Okay, so we're trying to do the antiderivative of this expression. You notice you have the square root of an expression in the denominator. It's almost always a u substitution. We're going to have to hope that this works out. Let's see what happens here. So I'm going to let u equal that denominator. Well, not the whole denominator, just the thing inside the square root, that expression. It's a little bit of lag here, so that's what it's awkwardly slow. Sorry about that. And then if we take the derivative of that, we get du dt equals, and we end up getting here, what, 6t plus 4t cubed. And I'm looking at this expression, and I'm really happy about it. And the reason is if I look at this and I look at the numerator, they're multiples of each other. You can see how perfectly designed this problem is. So what I'm going to do now is, well, we can see what we really need to do. Here's a way to do it. I can multiply this numerator by 2. If I were to do that, then I have exactly this expression down here. And I'm going to multiply by 1/2 on the outside to undo that multiplication by 2. So now we're ready. We can see that this whole thing on the top now, this whole thing on the top is really du, because I can multiply by dt over here. And then this expression in the bottom is just going to be u. So here we go. Let's do that. So we end up getting 1/2 the integral 1 over the square root of u du. And amazingly, let's finish this a little bit. Let's remember, let's do the antiderivative of this. We know from the previous problem we had gotten to this stage, and it ended up being right here. We ended up getting u to the 1/2. All right, so that's what we had. So we could do the same thing here. And so this is just going to be u to the 1/2. And so we're ready now. We can plug back in our expression. So if we were to do that, we would have the square root of 1 plus 3t squared plus t to the fourth. And we're going to evaluate that from -1 to 1. And let's see what nice thing happens. So if we were to plug 1 in here, we end up getting the square root of 1 plus 3 plus 1. And then if we were to subtract from that what we get from when we plug in -1, we end up getting 1 plus 3 plus 1 again. So we end up getting the square root of 5 minus the square root of 5, which amazingly is 0. So that's sort of interesting. So keep in mind that these line integrals compute sort of a net work that was done to you, a net amount of work that is. So maybe as we moved along this curve, we got some help in certain locations, and other locations we had the wind blowing in our face in a sense and doing work against us. So the net work done to us is 0. Now, how does it compare to the other path we took? Well, when we did our mathematics here, we got a different answer. So what does that lead us to believe? And I realized I could see an error here because in our previous example, for a second it looks like the work is different, but in our previous example, our lower bound of our integral was -1. And then somehow down here, you probably noticed it earlier in the video, I put 0. That was a mistake. This should have been -1. So if I plug -1 in here, -1 squared is 1, plus 4 is 5. So I get 5 under here. So this is the square root of 5 minus the square root of 5, which is 0. So for those of you who are watching and aggravated by me not noticing that error, I'm sorry about that. But it all resolved itself at the end. So what does that tell us about this vector field? Well, this vector field is special. And the reason it's special is that what we've seen is it didn't matter which path you took to get from the point -1, 2 to the point 1, 2, that in both cases, the work done was 0. So what we can say here is that between these 2 points, moving through this vector field, the amount of work done to you is independent of the path. We're leading towards this idea of path independence. Okay, great. Thanks for watching.